Welcome back, everyone, after the coffee break. I'm next speaker of the day is Michael Giudici. I hope I pronounced that correctly. From the University of Western Australia, and his talk is about synchronization hierarchy for permutation groups.
Hey, thanks. Thanks for the opportunity to speak. So, yes, I'm talking about synchronization for permutation groups. This is mainly just going to be a survey talk. So I don't know if you're familiar with this topic, then there's probably not much new for you, but if you're not familiar, then hopefully I'll be able to explain it all. So let's start. Right. So first of all, what is a finite automaton? Well, that's really just consisting of a set of states called omega, and then you've got a set of transitions between the states. And so these are just functions from your set omega to omega. Now, what do I mean by a reset word in your automaton? Well, this is just a finite sequence of transitions, which when applied to any initial state, results in the same final state. So I suppose the motivating idea, is you've got some piece of, some part going down a conveyor belt, and it may come in many different orientations, and you want your machine to always apply the same set of operations to that part to put it in the correct orientation. And so no matter which is the starting state it's in, you'll always end up in the right format. Okay, and so if your automaton has one of these reset words, then we say that the automaton is synchronizing. Now, I suppose the main conjecture in this area is the Černý Conjecture from the 60s, which says that if you have an automaton of length n, with n states, and you know that it's synchronizing, then okay, so it's synchronizing, there is a reset word, but the thing is your reset word should have length at most n take 1 all squared. Okay, so that's the Černý Conjecture. Now there's been lots of work on it. It's still open as far as I'm aware, but I suppose one of the nicer results on it is this result of Dubuk in 1998, and that is if you have an automaton which is synchronizing, and you know that one of the transitions that you have is a cyclic permutation of your set, then the Černý Conjecture does hold for that automaton. Okay, so that's one of the nice results for that. Now, I'm an algebraist, so I don't usually think much about automata. Okay, but if you want to think about it in an algebraic perspective, then we look in the setting of monoids. So you've got, given a finite set omega of size n, you can talk about the full transformation monoid on your set omega, and that's just all the functions from omega to omega. So I'm not assuming that they're bijections, I've just got functions from omega to omega. So they might be into omega, they might be onto omega. Now, then what's an automaton? Well, this is just going to be a submonoid of Tn, but you've got a distinguished set of generators. So they're the transitions that you're given. Okay, so you've got this set of transitions, and they're going to generate for you a submonoid of your full transformation monoid Tn. And then, well, when is your automaton synchronizing? Well, that will be if and only if your submonoid contains a constant function. Okay, so a reset word should be mapping everything to the same thing, so that's a constant function. And so if you can generate a constant function by your transitions, then your automaton is synchronizing, it's called synchronizing. Okay, so today I want to talk about, I suppose, what was put forward as an approach to try and tackle the Černý Conjecture, and that is via permutation groups. In some sense, well, a permutation group is a submonoid of your full transformation monoid, but everything in there is every function in that case is a permutation. If you have a submonoid, you can look at the permutations inside it. And permutations are not going to be constant maps. So your constant maps, your reset words, they're sort of like functions which must be outside your subgroup, right? I suppose it's called your units of your monoid. Now, so in some sense, the permutation groups are the monoids which aren't synchronizing, definitely not synchronizing. And so they thought, well, what you should do is instead of trying to prove things for monoids, we know much more about permutation groups. So let's look at a special case where you've got this nice subgroup inside the monoid. Okay, and so we call a permutation group synchronizing if any function f from omega to omega, which is not a permutation. If you take the monoid generated by G and this extra one function f, then that contains a constant function. Okay, so essentially your permutation group is synchronizing if whenever you add in one non-permutation, you get yourself a synchronizing monoid. Okay, and then the question is, well, which permutation groups are synchronizing? So that's our main question we want to look at. Now, there's a very nice survey paper by Arroyo, Cameron, and Steinberg. So I suppose this approach was suggested by Steinberg and Arroyo independently in about 2006. And since then, there was various work done by lots of different people trying to understand synchronizing permutation groups. And a lot of this is outlined in this survey paper. So a lot of results, if I don't attribute them to anyone today, like a lot of the basic lemmas, most of them are all coming from here. Okay, so first of all, what is a, how do we identify if a group is synchronizing? Well, there's this notion of a section regular partition. Okay, so if I have a permutation group G, then we say that a partition is section regular for your group G with section F. S, if I take any image of S under an element in my group, that's still going to be a section of my partition. So what I mean by a partition, that's just a section, that's just a transversal of my partition. Okay, so I've got a partition, I take a section or a transversal, so I've got one point from each part of the partition, and it's going to be section regular if I start with that section, and if I take any image of that section, I still get another section of my partition. And so, well, equivalently, I could fix S and then spin my partition under my group G, and I want my S to remain a section for every partition, which is an image of the original partition P. So that's what it means to be section regular. Now, I think this goes back to Arroyo. He proved that your group is synchronizing if and only if it has no section regular partition. Okay, so that would be how you could identify the group. So we've transferred, I suppose, the notion of having a constant function in a submonoid to just something about the action of your group G. Well, what groups are going to be have a section regular partition? Well, as a permutation group theorist, if you start talking about partitions preserved by your group G, then you have the notion of imprimitive, right? So this was mentioned in Gabriel's talk, but a transitive permutation group G is called imprimitive if there's some non-trivial partition preserved by your group. Okay, so here I've got a partition of my set. By non-trivial, I just mean that every part has at least 2 points in it, and you have at least 2 parts. So that's what I mean by non-trivial. And so if there is a partition which your group preserves, we call it imprimitive. If there's no such partition preserved by your group, then we call it primitive. Okay, so primitive permutation groups, they've been well studied, so we understand them very well. Now, again, an elementary lemma is that, well, synchronizing implies primitive. Okay, so every synchronizing permutation group must be a primitive permutation group. And why is this? Well, if I had a synchronizing permutation group which was not primitive, it's got this section regular partition. Okay. Sorry. If I have a I'll start again. If I have a synchronizing permutation group and it's not primitive, then it's imprimitive. So it's got this partition that it preserves. And if I take a section of that partition, any image of it is still going to be a section of that partition. Okay, because I'm preserving the partition. So therefore, any synchronizing group must be primitive. Okay, so that's synchronizing implies primitive, so that's good. Now, I think early on it was asked, well, is the converse true as well, right? If I know that it's synchronizing, if I know it's primitive, does that imply it's synchronizing? But it turns out that's not the case, right? There are actually primitive permutation groups which are not synchronizing, okay? So they still do have a section regular partition. So even though you have these groups which preserve no partition, they still can have a section regular partition. Okay, and so the standard example, I suppose, is a group which preserves a product structure on your set. So what I mean by this is you identify your set omega as a Cartesian product delta to the k. Your group G is inside the reef product syn delta reef sk. So this is the group which acts on here in product action. So I've got k copies of delta all acting on each of the k factors, and I've got sk transitively permuting the k factors round. Now, if I there's an obvious partition of P, which is given by, you just take everything which has a fixed alpha in the first coordinate, and that's one part of your partition. And for each alpha in omega, you get another part in the partition. Okay, so I'm just partitioning all the elements in delta of k up according to what their first entry is. Now, if I take any element in my group G, since it preserves the product structure, it's going to map a partition of this form to a partition where, instead of now we're partitioning by the first entry, I could get to a partition where I'm partitioning by the second entry or the third entry or so on like that. And they're the only possible images of my partition P. And if I just take all the constant k tuples, then that's going to be a section of this partition P, but also a section of any other partition which is an image under P. Okay, and so these groups are not synchronizing. Now I should say, of course, if I took the full Reef product here, that's a standard example of a primitive permutation group. So these are primitive permutation groups, and even though they do not preserve any partition, they still do have section regular partitions. So not all primitive groups are synchronizing. Now, the next thing to look at, well, one big class of primitive permutation groups are the two transitive ones, and there's also the notion of the two homogeneous group. So a two homogeneous group is just one which is transitive on two subsets. So if I have any two subsets of my set omega, I can map the first two subset to the second. And also two transitive, now instead of acting transitively on two subsets, I'm now transitive on ordered pairs of distinct elements. So clearly if I'm transitive on ordered pairs of distinct elements, I'm also transitive on two subsets, but not necessarily the other way around. Okay, so two transitive implies two homogeneous. Now, any two homogeneous group actually has to be synchronizing, because if I have a two homogeneous group, and let's suppose I have a partition P with a section S, well, I can take 2 points in my section, so alpha and beta are going to lie in different parts of my partition, and then I take 2 points lying in some part of my partition. Well, then there's some element in my group which can map this pair to this pair, and therefore it's mapping my section to something which is not a section because it's got 2 points in one part. Okay, so if I'm two homogeneous, there can't be a section regular partition, and so my group must be synchronizing. So that's what we have for synchronizing. So we have this like nice chain of implications, which is going to be my hierarchy of synchronizing groups, but my hierarchy, I'm going to build it up as we go along, and this will get larger and larger. And so we know that two transitive implies two homogeneous, which implies synchronizing, which in turn implies primitive. Okay? And so one thing we always want to know is, well, what groups lie in these classes? Okay, and how do these classes differ? So there are two homogeneous groups which are not two transitive. So this is a proper containment. We've seen that there are primitive groups which are not synchronizing. And equally, not every two homogeneous group is, not every synchronizing group is two homogeneous. Okay, and a standard example is you take Sn acting on two subsets. That's another nice primitive action. And for n odd, that's synchronizing, and it's not two homogeneous. So that shows that these four classes of groups are all distinct classes. Well, there's another related notion called separating, and this, I suppose, is motivated by this old lemma of Peter Neumann. It says if I take two subsets of omega, such that the size of their products is less than the size of omega, then there's always some element in your group which separates them. Okay, so there's some element in your group such that A intersect the image of B under G is the empty set. Okay, so that's what happens if you have the strict inequality here. And so the question you may ask, well, what happens if I have equality here?
Michael, can I ask a quick question?
Yep.
Is there any hypothesis on this theorem at all? Like any group action or transitive or what? Or
you do need transitive, yes. Yep.
And that's it.
That's it.
Okay.
Yes. Yep. Sorry. Yes, I didn't put that in the thing. I've just got G here, which is a random G. Yes, that's a transitive group. Yes. Sorry. Okay. So we have this separation. So then we can call a group separating if I have any two subsets A and B which are not singletons and whose product is the whole product of their orders is the size of the whole set. Then there is some element G which separates the two things. Okay, so right, this always holds if we have the order of this product is less than the order of omega, but we're interested in a case where we have equality. And so if whenever you have two sets A and B, the product of their orders is the order of omega, if you can always separate them, you call your group separating. So that's what we mean by separating permutation group. Now, any separating group must be synchronizing, okay? Because if not, you take a section regular partition for it, and you take a block. Well then, if I take the size of a section times the size of a block is going to be the size of the whole set. And then if I just take any image of my section, that should still be another section, and therefore it must intersect my block in one point. Okay, and so I'm not getting separation. So therefore, any separating group must be indeed a synchronizing group. And this also then gives us some more examples of synchronizing groups, because if I have a transitive group of prime degree, the size of my set is a prime, it's got no proper non-trivial divisors, and so trivially I'm going to be separating, and hence trivially I'm synchronizing. So that's good. I suppose I should also give you an example of a separating group other than of prime degree. Again, if we go back to Sn acting on two subsets with n odd, this is another example of a separating permutation group. So that's what separating is. Okay. Now, yes, at this point it's because I realized early on in my talk that I did have that my slides nicely progressed, but I had it in handout mode just before I looked at it. So we're in handout mode, so you get to see everything at once. I'm not doing the slow reveal. But anyway, so there's another lemma that actually, if I have my group is not separating, okay, then for any pair of subsets, not both singletons, sorry, which are not singletons, and the order of their product is the order of a set, then we have that the order of A intersect any image of B is always 1 for all G in your group. Okay. Now, this lemma is disproved by, I suppose, a bit of counting. Effectively, what you can show is that if you have this equality here, then the average size of this intersection is always 1. And since it's not separating, there's nothing which has size less than 1. And so therefore, there can't be anything with size bigger than 1. So all your sizes must be 1. Okay, so that's what we have this nice lemma. Now, that then motivates the following definition, where we now say that a transitive permutation group is non-spreading if there's some subset B and a non-trivial multiset of omega and a positive integer lambda, such that the size of A divides the size of omega. And if I take the characteristic vector of A and the characteristic vector of the image of B, and I take their dot product, then I always get lambda. And this happens for every element in my group. So I suppose this is generalizing the notion of not separating, okay? Because if I have a group which is not separating, if I just take A to be a set of this form here, okay? If I take B, so I take B to be a subset, A to be a set, such that the order of A times the order of B is the size of omega. So that means I have this divising property. Then this is always equal to 1, okay? And so a non-separating group is non-spreading with lambda equals to 1 and taking a set instead of a multi-set. Okay? And so spreading does imply separating. Now, we can't go, the converse is not true, because if I go back to my example of Sn acting on two subsets, okay, we've seen that I said it was separating, but it's not spreading. Okay, and this is because if I just take the following set of n two subsets, so I just take 1, 2, 2, 3, 3, 4, and so on, all the way down to n minus 1n, and then n1. And so that's a set of size n. I'm going to take B to be the n minus 1 pairs which all contain 1. And if I look at all the images of B under an element in my group, well, B is all the pairs which contain 1. Then the images of B is going to be all the pairs which contain 2, or all the pairs which contain 3, and so on. And so any image of B always intersects my set A in two subsets. So I've always got this equality here. Okay, and so therefore it's not spreading using lambda is equal to 2. So there's an example of a group which is separating but not spreading. You can show that any two homogeneous group is spreading. So there are examples of spreading groups. And so what does our hierarchy look like now? So I've added a few extra definitions in, right? So we have two transitive groups, they imply two homogeneous, they imply spreading, they imply separating, which implies synchronizing, and which implies primitive. Now, instead of looking at the implications, well, what do these sets of groups have, right? So any two transitive group is two homogeneous, any two homogeneous is spreading. But I've said that there's examples here which are not there. But at the moment, I haven't given you any spreading groups which are not too homogeneous, so I've left the equality sign here. Spreading is contained in separating, and Sn on two sets is separating but not spreading, so I've got a strict inequality here. Separating is contained in synchronizing, but I haven't given you any groups yet which are synchronizing but not separating, so I haven't, I've still got the equality here. And synchronizing is contained in primitive. right? And that's a strict inequality because I've given you those groups preserving a product structure of primitive, but not synchronizing. So that's our hierarchy that we have of groups. So one thing we want to know is, well, we would like to answer, say, these things here, like are these inequalities strict or not? Well, one, I suppose, amazing thing about this topic is actually there seems to be connections with many other areas of combinatorics and mathematics. So, sorry, my phone is ringing. So hang up and keep going. So, right, my office phone never rings. So of course it wants to ring when I give a talk. So, okay, so connections with graph theory. So one area where there's many connections is in graph theory. So there's a few standard graph theory parameters which are very well studied. So I have a graph gamma. I can look at the clique number, and that's denoted by omega of gamma. And this is the size of the largest clique. So by clique, I mean a subgraph, which is a complete subgraph, right? So I've got vertices all connected, all adjacent to each other. There's also the independence number, which is denoted by alpha. And this is the size of the largest independent set. So by an independent set, I mean a set of vertices which are mutually non-adjacent. So I want the largest size of one of those. There's also the chromatic number. So usually chi of gamma. And this is the least number of colors needed to color the vertices, such that no two adjacent vertices have the same color. Okay, and so these three parameters are widely studied in graph theory. Obviously, your chromatic number has to be at least the clique number, okay, because if I have all the vertices in the clique, they're all adjacent to each other, so in any coloring, they're going to have to be given a different color. So you've always got this inequality here. Now, if you look at the notion of, we want to introduce the notion of graph homomorphisms. So what do I mean by a graph homomorphism? Well, here now I have two graphs, gamma 1 and gamma 2, and I say, what's that homomorphism between them? It's just a map from the vertex set of the first to the vertex set of the second. So I'm just saying a map, so I'm not wanting it to be a bijection, such that if I have an edge in the first graph, it gets mapped to an edge in the second graph. I'm not saying anything about where the non-edges go. I'm just saying that edges must go to edges. Okay, and so this is called a graph homomorphism. If it was a bijection, then it would need to be an automorphism. Now, there's a standard lemma that says that if I have a homomorphism from KR, so this is the complete graph with R vertices, to my graph gamma, well, that only happens if and only if my clique number is at least R. Okay, because my R vertices of my complete graph are going to have to go to R vertices which are all mutually adjacent in gamma, and so they're going to have to be a clique in gamma of size R. And so therefore, my maximum size as a clique will be at least R. So that's the first one. The second one is that, well, there's a homomorphism from gamma to your complete graph. So this is going in the other direction, if and only if your chromatic number is at most R. So to see this, I suppose you just think of your homomorphism from gamma to KR as being a coloring of the graph, right? So for each vertex in KR, you give it a color, you assign your vertex in gamma the color of the vertex it gets mapped to, right? And then if I have two vertices which are adjacent in gamma, they're going to have to go to different vertices down in KR, and so they must have been assigned different colors in the coloring. So that's why you have that your chromatic number is at most R. Anyway, so then you can show that your group is synchronizing if and only if there is no non-trivial G invariant graph whose clique number is equal to the chromatic number. Okay, so for any graph I said before, you've always got the clique number is at least the chromatic number. Okay, but to be synchronizing, you don't want equality to hold. Now, well, to see that, if we go in one direction, so if I have equality here, then that means I've got a homomorphism from gamma to KR, and then another homomorphism from KR back to gamma. So if I compose those two homomorphisms, I'm getting a homomorphism from gamma to gamma, and that's not going to be a permutation because I've gone down to assuming my graph is not complete to begin with, then I've got a homomorphism which is not a permutation. So I've got myself a function which is not a permutation. And then if I take the monoid generated by G and this new homomorphism, this generates for me something which is contained inside the endomorphism monoid for my graph gamma. And the endomorphism monoid for my graph gamma can't contain a constant function. Okay, it's not possible to have a graph which has edges in it. There's no homomorphism from that graph to a single vertex. So that's why your group has to have been synchronizing. Okay, so your group is synchronizing if and only if you have no non-trivial G-invariant graph whose clique number is the chromatic number. Now, why are we interested in this? Well, for many groups, it's quite easy to work out the G-invariant graphs. Okay, I can look at the orbital digraphs and then get the G-invariant graphs from them. Right, any G-invariant graph is just a union of the orbital digraphs. And so in some sense, this gives us a nice computational test if a group is synchronizing. We don't need to go looking for section regular partitions. We don't need to throw in extra functions and see if we have a reset word. Okay, we just need to construct all the non-trivial G-invariant graphs. I say we only need to, but if we can, we construct all the non-trivial G-invariant graphs. We calculate their clique numbers and we calculate their chromatic numbers. Again, that may be hard, but we hope that it's doable in many cases. And then that's an easy test for synchronizing.
Sorry, may I ask a question?
Yes.
Yeah, so this G-invariant graphs, are we talking about, what do I want to say? Are we considering, because given a graph, one can just define a trivial action on.
Sorry, when I mean G-invariant, I meant, so G is a permutation group on a set omega, and I'm having a graph on omega which is invariant under that permutation group G. So G is inside the automorphism group of that graph.
Oh, I see. Okay.
Sorry, that's what I meant by G-invariant. So my graph is constructed on the same number of points that my group G is acting on.
Okay, thank you.
Thanks. Okay, so we've converted the question of recognizing if a group is synchronizing just to a question about studying the graphs that it acts on. Now, we can do something similar for separating groups. So here now, a graph gamma. There's a standard lemma in graph theory which says if I have a vertex transitive graph on n vertices, then the independence number times the clique number is at most n, where n is the number of vertices. And moreover, equality holds if and only if any clique and any independent set of maximal size has non-empty intersection. So I mean both the clique and the independent set have maximal size there. Okay, so if I have any clique, any independent set of maximal size, they're always going to be intersecting in at least one vertex. And well, it turns out that your group is separating if and only if there's no non-trivial G-invariant graph where you have equality here. Okay, so where the clique number times the chromatic number, sorry, the independence number times the clique number is the size of your set. So how to see this going in one direction. So I suppose if your graph does have this property, right? If there's a G-invariant graph with this equality holding, you just take A to be a clique, you take B to be an independent set of maximal size, okay? And by this lemma, it tells you that any other independent set of maximal size must have non-empty intersection with your clique A, and the image of any independent set under an automorphism is still going to be an independent set, so you always get non-empty intersection. Okay, so that's why this would imply that if there is such a G-invariant graph, then you're non-separating. So many results in this way, you always prove them by proving the contrapositive instead of a straight way. Then for the other direction, okay, if I have two sets A and B, which I can't separate, okay, then what I do, if I form a graph whose edges are all the images of pairs of elements in A. Right, so every pair of elements in A is an edge, and then the image of those pairs are also going to be edges. And so then A is going to be clique in this new graph. Gamma is going to be G invariant. And I know since I'm not separating, A under any image of B always has size 1. And so I'm never getting an edge properly contained in B. So therefore B is an independent set. And then so the size of the clique number is A, the independence number is the clique number is the size of A, the independence number is the size of B, and their product is the size of omega. So that's how we get that. So again, we also have a nice algorithm for testing separating. So we've got nice graph theory algorithms for testing separating and synchronizing. But I suppose someone like Gordon would tell me that finding the clique number of a graph is very hard. The vertex transit graph, it's a bit computationally easier, it turns out. Lendensoicher has gone up to all permutation groups of degree, all primitive permutation groups of degree up to 255, and has worked out whether or not they're synchronizing or separating. Okay. So that's good in those cases, but for spreading, we don't have any nice graph theory test. So we actually don't have any nice, I think, as far as I'm aware, we don't have any nice algorithm for testing if a group is spreading or not. Okay, so that's connections to graph theory. So if we go back and look at our hierarchy again, right? So I've got two transitive implies two homogeneous, implies spreading, implies separating, implies synchronizing, implies primitive, okay? And then the inclusions that I mentioned before. So if we're trying to understand these synchronizing groups, okay, one way I said, well, we could look at the graph theory way. That's going to give us a way to computationally check certain groups. But we know a lot about primitive groups, okay? We know a lot of theory about them. So what happens if we try and apply some of that theory about primitive permutation groups to the synchronizing problem? Well, okay, we have the Yonan-Scott theorem for primitive permutation groups. And it tells me if I have a finite primitive permutation group that does not preserve a product structure, then it's of affine or diagonal type, or it's almost simple. Okay, so affine type, I just mean it's a subgroup of the affine general linear group. Diagonal type, well, there's this diagonal action. Essentially, your group has this minimal normal subgroup T to the K, but point stabilized, and that is just a diagonal subgroup. So it's just a subgroup isomorphic to T and projects onto T in every coordinate. Or your group is an almost simple group. Okay, so that means structurally it's an almost simple group, abstractly. Right? It's strictly between your simple group, so not strictly, but it contains the simple group T as a normal subgroup, and it's contained inside the automorphism group of your group T. Okay, so any primitive permutation group, if it doesn't preserve a product structure, it's one of these three types. Now, we could then look at these three types and try and analyze them to see if it's possible for a primitive group of these types to be synchronizing. And in the diagonal type case, now very recently, there's a paper by Bray, Chai, Cameron, Spiegel, and Jung, who showed that if you had a synchronizing group of diagonal type, then a minimal normal subgroup of your group is of the form T squared, or T a finite non-abelian simple group. So there's diagonal type groups where your minimal normal subgroup is T to the K for any K at least 2. And they show that to be synchronizing, we actually need to have T squared. There are actually examples here. There's a construction of Peter Neumann, which shows if your simple group T can be factorized, has an exact factorization, then you can get yourself a synchronizing group. So that's, so in some sense, we think the diagonal type case is very well understood. The affine case, I'll say a bit more about the affine case later. But another thing that these group of 5 proved is that if I have a primitive permutation group which is not almost simple, then it's synchronizing if and only if it's separating. Okay, so if I in my hierarchy, if I go back to my hierarchy here, okay, at the moment I still haven't given you any synchronizing group which is not separating. And so by this theorem, if there is such a group, it has to be an almost simple group. So that's what we have there. Okay, so this sort of gives us some guidance as to what to look for, right? If we're looking for groups in that hierarchy, we should probably concentrate on the almost simple groups. Now, we've talked about SN acting on 2 subsets. We can also look at SN acting on K sets. This is a standard primitive action. And there's been various work looking into when this action is synchronizing or separating or spreading. Okay, so as I said, SN on 2 sets, it's separating if and only if n is odd. Well, I said earlier that it was separating if n is odd, but that's actually an if and only if. If you look at SN on 3 sets, well, again, we know that completely. It's separating if and only if n is 2, 4, or 5, 1, 6, and n is not 8. And actually, to prove that, this uses the famous theorem of Tierlink about the existence of a partition of all 3 subsets into Steiner triple systems. So Steiner triple systems, these are a famous combinatorial object, which are well studied. It's just a a Steiner triple system is just a collection of 3 subsets, such that every 2 subset is inside a unique 3 subset. Okay, and then TIA-link worked out for which values of n you can partition all the 3 subsets into lots of Steiner triple systems. So that's what we have there. You can also show that if k divides n, then Sn on k sets is non-synchronizing. And this also uses a famous combinatorial result of Baranyai, which talks about the existence of a partition of all k subsets such that each part is a partition of 1 up to n. So here. And also recently, so Kivash proved that Steiner systems exist for all the parameters where you expect them to exist. And so his result then also gives you infinitely more values of n and k, for which Sn acting on k sets is non-separating. Okay. So Sn acting on k sets, it's a fairly, I suppose, from a permutation group theory perspective, it's a fairly nice or easy action to consider, because you know everything about Sn, you're just acting on k subsets. But to actually determine if the groups are separating or synchronizing, it actually seems to use a lot about famous examples of famous results about existence of certain combinatorial structures. So there's lots of links to lots of other area of combinatorics there. I should also say that these groups are always non-spreading. You just like generalize the argument I gave you for why Sn on 2 subsets is not spreading, and that works. So that's Sn acting on k sets. That doesn't help us in trying to fill in our hierarchy vote. Right, we're still looking for groups which are too homogeneous, which are spreading but not too homogeneous, and synchronizing and which are not separating. So to do that, I've got to go now to finite geometry. Okay, so again, there's many connections with all of mass, so finite geometry appears. And so here for finite geometry, okay, so we have our classical groups, finite classical groups. So these are things like you have a finite analog of the orthogonal groups, the unitary groups, the symplectic groups. And their natural actions is on what's called a polar space. And these are analogs of projective spaces. Essentially, instead of taking all the subspaces of your vector space, you just take the totally isotropic or the totally singular subspaces. Okay, so your orthogonal group, you've got a quadratic form. And so you can take all the subspaces upon which the quadratic form is 0. They're all your totally isotropic, totally singular subspaces. Or you have your unitary form, you take all the subspaces upon which your unitary form restricts to the 0 form. So you take all these subspaces and study them by inclusion, and you get a polar space. And so that's the analog of your projective space. And your classical groups act nicely on the polar spaces. Now, Cameron and Kazanidis in 2008, they made the following observations, that if I have a classical group in its natural actions, that means on the points of your polar space. So this is an action on totally singular 1 spaces. Then this action is non-separating if and only if its polar space contains an ovoid. And it's non-synchronizing if and only if your polar space, either it contains an ovoid and contains a spread, or it has a partition into ovoids. Now, I didn't want to say what an ovoid or a spread is, but I did want to say that these have been well-studied objects in finite geometry. There's been a lot of work into trying to work out the existence of them. But there is still some polar spaces where the existence question for ovoids is still open. Okay, but when we do know that they exist, we can say that these groups are non-separating. There's also a lot of work on spreads, and when they exist, there's been far less work into trying to know when you can actually partition your polar space, the points of your polar space, into ovoids. And again, these are nice geometrical questions and have been well studied from a geometer's point of view. Okay, and indeed, there are some results. So Simeon Ball has shown that, so in Q4P, this is an example of a polar space. So this is coming from a 5-dimensional vector space where you have a quadratic form acting on it. Okay, and he's shown that in this space, the only ovoids are what are called elliptic quadrics. And then previously with Storm and Govertz, he'd shown that any ovoid had to intersect an elliptic quadric in 1 modulo p points, which means you can't get a partition into ovoids. And so therefore your groups are synchronizing, but not separating. And so now finally I've provided some examples of synchronizing groups which are not separating groups. Okay, and it's quite, I suppose, amazing that we went to these nice results from finite geometry, which even, Simeon Ball's result was like a very famous, striking result for the finite geometers, but actually gives us examples now of synchronizing groups which are not synchronizing. Sorry, synchronizing groups which are not separating. So we get one for every prime p. Okay, so that's good. Now my hierarchy of groups, I've got a strict inequality here. So that leaves us in this gap here, right? I haven't given you any spreading groups which are not too homogeneous. So I've done combinatorics, I've done finite geometry. Let's do some representation theory. So if I have a permutation group G, you can take the permutation module. So this is just the vector space. So I've got the number of coordinates is the number of points in my set. My permutation group is just permuting the coordinates, and I'll be over a field of characteristic 0. Now, my permutation module always has this natural decomposition. I've got the constant module, and I've got what's called usually the augmented module. So these are just all the n tuples who sum to 0. And these two things are intersect in a 0 vector, and they give me a direct sum for V. Right? And these are both submodules of the permutation module, so they're G invariant. Now, I suppose one of the first results you do when you do representation, the permutation module, is that if I take F to be the complexes, then your permutation group is 2 transitive if and only if W is irreducible. And if you take F to be R, then your group is 2 homogeneous if and only if W is irreducible again. Okay, so you can transfer results about the irreducibility of W into whether or not your action is 2 transitive or 2 homogeneous just by taking the appropriate field. Well, another field of characteristic 0 is the complexes. And so you could also ask, is this W irreducible when we just look at the complexes? And in that instance, it's what we have called a QI group. Okay, so a group is a QI group if your augmented submodule is irreducible, then you're over the rational, sorry. And it turns out you can show that a QI group must be spreading. Okay, so any QI group is spreading. Okay, so this then motivated Dixon to study QI groups. I think Ben Steinberg asked him to study QI groups, and he was able to show that a QI group is primitive. It's got to be affine of almost simple type. And he also classified the affine ones. Okay, actually turns out they're just not far from being 2 transitive affine groups. Okay, and then John Bernberg, myself, Martin Liebeck, Cheryl Prager, and Jan Saxel in 2013, we actually classified all the almost simple QI groups. And the only non-2 homogeneous ones, they all have so-called PSL2, 2 to the F, acting on 2 times 2 to the F plus 1 points, but with 2 to the F take 1 prime. Now, we actually didn't start out trying to classify the QI groups. We were actually studying something else. We were studying what are called 1.5 transitive groups, and we classified all the almost simple ones of those. But it turns out that any QI group is 1.5 transitive, and so by classifying all of those, we were able to get the almost simple QI groups. Okay, so we know all the QI groups. And indeed now in our hierarchy, I can stick QI in between spreading and 2 homogeneous. There's one infinite family strictly in here, but not in there, so I get that. And so this is now, I've separated 2 homogeneous away from spreading. And so I've got, by sticking QI there, but I don't know about here, right? And in fact, actually that's still an open question, right? There's no known examples of groups which are spreading that are not QI. It would be great if you had equality there, because in some sense, it's easy to test if a group is QI because we know the list. Equally, you just look at the permutation module, but we actually have no nice algorithm for testing if a group is spreading. So it would be great if we had equality there, but we don't know. Sorry, so there's no known examples that are spreading and not QI. So I just wanted to finish with a few open questions about what, I suppose, what you would like to do when looking at this hierarchy of groups. Okay, so first of all is QI equivalent to spreading? That's the first thing, right? We'd want to know, is our hierarchy really a proper hierarchy, or are these 2 classes just the same with very different definitions? I mentioned affine groups, so I haven't looked at them much. It turns out for affine groups, QI is equivalent to spreading, and separating is equivalent to synchronizing, but we don't know if these two collections then are the same or if we have a proper inclusion. Okay. For two-dimensional affine groups, then we know the answer is yes. These are all four concepts are all the same thing, but in general, we don't know. We don't have any, well, yeah. We'd like to show that this is, either we'd like to show that these are all the same, or we'd like to have a nice construction of separating groups which are not spreading. So that's there. And I suppose the last thing is just always good if you can find more examples lying in each of the layers. Okay? So often to do this, it usually requires some nice other mathematics, like we saw in finite geometry was a good one for classical groups. For SN acting on K-sets, we're using lots of nice things about the existence of Steiner triple systems and the like. And so another thing that we want to do would be looking to see, can we just, for your favorite primitive permutation group, can you work out in which layer should it be? Should it be synchronizing? Is it spreading? Is it separating? And that's the main thing. And that I seem to have frozen. Oh. Right, yes, so that's the end. Yes, thank you.
Thank you, Michael. Do we have any questions for Michael?
Just a small one. Michael, I was curious, these open questions at the end here, is that mostly what your discovery project is about?
Oh yeah, so these are the things we want to look at. So one, we want to do a lot, definitely this, the last part.
Right.
Like trying to work out the layers.
Yeah.
One thing we want to do is also the classical group question. So we have like John's a finite geometer, and he's very much interested in like the existence of ovoids and the existence of spreads and things like that.
Good.
And so if he can answer some of those questions, then we'll be able to answer questions about putting groups in the certain layers. So that's one thing we want to do. We're very much interested if we can answer this question. That would be good. If we can somehow find a spreading a group which is not QI, would be great. Yeah.
Very good.
And do we have any other questions for Michael?
Yeah, we've only just started, so we don't really have any new results to announce at this point.
Sure.
Perhaps we've identified one new synchronizing group or two new synchronizing groups might be.
So perhaps you're hoping to put some sort of atlas of putting all the groups within appropriate layers.
Yeah, that's right. Yeah, ideally we'd want to be able to do that. There's still many other, well, for example, even the classical groups, I only talked about their natural actions on points. They have lots of nice geometric actions. So you'd like to translate those into the synchronizing, separating, spreading hierarchy and work out what geometric properties you need to work out where they land.
Yeah, very nice. So if we don't have any further questions for Michael, let's thank him
I had
again.
a quick question. So with the groups that are QI, but are not too transitive or not too homogeneous, is there sort of a natural smallest field under which you get the module breaking up? Do you get any interesting like field structure there?
What do you mean by natural smallest field? The Q's as small as you can go for characteristic zero, isn't it?
No, so I mean it's irreducible over Q, but it splits over C. So like, you know, what kind of irrational elements do you need to add to your field to make it split? Do you get any interesting structure there?
Well, we could probably work that out because we know the groups exactly. So yeah, I suspect we could work that out, but I haven't looked at it. Yeah. Yeah, because it's just one family of groups. You know what they are. You can work out the permutation module, and you can work out what roots you need to join to Q to get the splitting. So.
Okay. So let's thank Michael and see everybody in 2 weeks.